Hello, ladies and gentlemen, and welcome back. Thank you for joining me. We're looking at question, or should I say problem number 4 here on our 2011-2012 Alberta math contest, specifically problem 4 of part 2. So we're almost done, although I do find the last couple questions can be more challenging, but that's just me. It looks like we've got a geometry question here. So, in triangle ABC, AB is equal to 2, BC is 4, and CA is 2 root 2. So that should be sort of enough to work out. We have BC down here, that's the longer one. 4, and I guess this is a 2 root 2. That should be enough to work out the whole triangle. You know the three sides, you should be able to work out everything. I mean, that's the whole idea behind trigonometry, isn't it? So, we've got our whole triangle. What have we got? P is a point on the bisector of angle B, chosen so that AP is perpendicular to this bisector, and Q is a point on the bisector of C, so that AQ is perpendicular to this bisector as well, and we want to know the length of PQ. What? All right, let's draw a big version of this triangle here. Oops. I lost focus there. There we go. So let's get a big version of this triangle here. All right, so we'll keep A, B, C here. This is the 4, this is the 2 root 2, this is the 2. And then we have the bisector, so angle bisector of B. That's something coming along out here. P could be outside. It could be, P makes a right angle there. It doesn't look like it from the picture I've drawn, but it's not exactly like my picture is exact. But, okay, bisector, it splits this in half, and P is chosen so that we get a right angle there. And then we bisect C. Angle over here at C. That's a little too shallow. Again, no idea where it's going to go, but little crosses here. And then it is AQ, right? Yeah, AQ is perpendicular. So we almost, if you call this middle point here R, we have a cyclic quadrilateral APRQ. So that's something worth noting. Now, what do we want? We want the length of PQ, or QP, I guess, because I've got them working backwards here. Okay. So what can we do here? I don't even know if P and Q are inside this triangle, but I want this length here. Now the fact that I got this little triangle APQ up top, I mean, maybe we can work with it, but I don't quite know how to get to the side lengths involved here. I'm just going to shorten these. And I don't know if I need this intersection point here. We'll remove it for now. But okay, so that's the idea. Now if I look here, got a nice right angle triangle. And what I said before was true. We do know all the sides, so you can actually work out what this angle is, and therefore what this length is, and this length is. And then you probably could work out this length, and then there's some overlap there. Now, I don't think that's necessarily going to be the way to approach this, because remember, you can't use calculators. So although knowing that we've got a 2, a 4, and a root 2 here means with cosine law I can figure out this angle, and therefore cut it in half and get these little dots here, we wouldn't be able to get it sort of exact. We'd have to do something like, 2 squared, so 4 minus 16 minus 8 all over 16 root 2 is the cosine of twice dot, so the cosine of b. Is that going to be something that's nice? 4 minus 24, so that's negative 20. Divide top and bottom by 4, you'll get to negative 5 over 4 root 2. Yeah, that's not a nice angle. But that is an option. We could... It's definitely a plan of attack. Get that angle. Similarly, get the little X angle here. You should be able to then get this check up here, and then you could do another... So once you've got this side and then this side over here, do another cosine law, and that'll get you PQ. That could do it. But because we can't use calculators, I lean less towards trigonometry for something like this, and I wonder if there is a geometry way to do it. Okay? We could slog through and figure out, we could get an exact expression, most likely. Just a question of, is that going to be a nice exact expression? But we do have this right angle triangle up here. Another one up here, and I'm focusing on the right angle triangle part of it. We do need to remember that these came from angle bisectors. So, yeah, we got this dot here, but is there something to do with this dot here? I'll tell you what, because it's a right angle, if you keep going AP and it intersects, and I don't know, we'll call this R. Now we'll call it D, because I already mentioned R in the video, and we might need this here for a moment. So we'll call this D, and I guess you could call the next one that we make E, but you'll get a right angle here, and so ABP and DBP are congruent. So that would make this 2 root 2 here. And you get a 2 here. Now, obviously, you got this little bit of an overlap. Call this E, I guess. Then PQ. So I like that. I like that we got those angles. And with the total 4, we can figure out this overlap. Oh, and PQ are going to be midpoints because they're congruent. So this is equal to this, and this is equal to this. And so if they're midpoints, then PQ is half of ED, which I can work out because it's this little overlap between the blue and the green, and I know the total is 4. Okay. All right. So I have a plan of attack. This one looks a little nicer than using cosine law. Not that you couldn't use cosine law. Without a calculator, I think it would be a bit of a pain. But let's say something like this. Extend AP and AQ until they meet BC at D and E respectively, which is what I have over here. Okay. So now we've got to justify the congruency. So angle ABP is equal to angle DBP because BP is a bisector. And angle APB is the same as angle DPB is 90 degrees because we extended AP. So triangle PB is similar to triangle APD, but they both have side BP in common. So in fact, APB is congruent to APD. And you don't have to repeat the argument, you can just say similarly, AQC is congruent to, oh, it's not APD, it's BPD. No, DPB. DPB. So, there we go. Had my triangles wrong. And so this would end in C, but it'll be E. Okay. So there we go. I've done my construction. So that means that now 4 is BC, which we can see is BD plus EC minus DE. Although we haven't really shown that this is the right picture, that D, because what if it's really weird and it's B and D and E and C and there's actually a gap here. So here's what I'm gonna, so we gotta make a little bit of an argument first. So we'll say BD is the same as BA, which is 2 root 2. EC is the same as AC, which was 2. Yes, 2. 2 root 2 plus 2. 2 root 2 is about 2.8 something, plus 2 is greater than 4. So we'll say it this way. BD plus EC is equal to 2 root 2 plus 2, which is greater than 4, which is BC. So we see B, E, D, C lie in that order. Right? Yeah. Because there's no way D will be outside. Yeah. Okay. So we see that ED is BD plus EC minus BC, which is 2 root 2 plus 2 minus 4, which is 2 root 2 minus 2. Okay. So now I've got that, 2 root 2 minus 2, but then we also know that AP is PD, and AQ is QE. So P and D are the midpoints of AD and AE respectively. So PQ, well actually it should be QP, is 1/2 of ED. This is a nice true fact. Anytime you got a triangle and you've got, say, x, well, 2x here, and you take the midpoints, it'll be a regular x. Just like if you had, more generally, if you have any triangle and you've got a ratio of 1 to k on the sides, and this is k plus 1 times x, then this will be regular x. Okay? Just so happens we're doing it with the case of 1, 1. I mean, you can say that you don't have to just jump straight to this. You could make the argument with similar triangles or whatever. I think you're going to be fine like this. Okay. So, that's a half of what did we just work out? 2 root 2 minus 2. So it should be root 2 minus 1. And if you wanted to, I mean, putting the box is fine, but you can say PQ is root 2 minus 1 here. And that would work just fine. Now, I like that that's a nice exact answer. And we would get that same nice exact answer if you did a whole bunch of trig work with the cosine law, which is what I originally planned. And the only reason I didn't follow through on that is just because, well, you can't use a calculator. So unless the angles were nice right off the bat, not something you particularly want to do. Okay. But, if somebody did do it with trig and not using a calculator and therefore not simplifying, so keeping whole jumbles of expressions together, please, by all means, in the description, let me know. Let me know how it went. Was it as nice and quick as the easy geometry there? Or, was it sort of a nightmare to be avoided? But I think we're going to call it quits there for problem number 4. It was a nice little problem. It wrapped up sooner than I usually get for problem number 4. I don't know, maybe this year was easier or something. I don't know. We got one more question to go. That'll be problem number 5. So we will finish off part 2 of our Alberta paper next time. I'll see you there.